Good evening, everybody. I will be talking about the influence of environmental and population factors on herring spawn timing in Prince William Sound. But first, let's put a face to the slides. I'm Beatriz Diaz, and I'm a postdoc at the School of Aquatic and Fisheries Sciences at the University of Washington. This work is in collaboration with David McGowan from the Alaska Fisheries Science Center and Trevor Branch. Let me transport you to our study region, Prince William Sound, located in the central northern portion of the Gulf of Alaska. Prince William Sound is a unique place with glaciers and marked by 12 distinct ecosystems. Unfortunately, Prince William Sound is still dealing with the consequences of the 1989 oil spill, which deeply affected the marine and onshore ecosystems with a range of wildlife, including the local Pacific herring population. So, 3 years after the oil spill, the Prince William Sound Pacific herring population suffered from a steep decline, which is thought to be caused by several hypotheses, including the event per se. But one of the most pressing factors is that the population was already facing a poor recruitment event in '88, which was definitely amplified by the '89 oil spill. In this graph, we have years in the x-axis and the spawning stock biomass in metric tons, 1,000 metric tons, in the y-axis. This population is also, a recent study showed that this population is the one that is suffering the longest lack of recovering from all these global studies on all herring populations in the world. And that goes to our question: what is impeding Prince William Sound herring recovery? And what are these recruitment bottlenecks? And more importantly, what is causing them? So for our study, we are focusing on the spawning portion of the Pacific herring life cycle, more specifically, the spawning timing. The herring spawning shows variable patterns, as you can see in this short video, where there is a downwards and eastern shift. The two different colors, they show the eastern and western portions of the Prince William Sound. And besides the shifts on spatial patterns over the years, my colleague David McGowan also found a strong temporal variability for Prince William Sound, where spawn timing shifts up to 2 weeks. As in nature, time is everything, we are exploring the causes of this variability. We use generalized linear and additive models as our methodology approach to further investigate which population, environmental, and climatic variables have the most influence on herring spawning phenology. Our goal is to provide information to stock assessment and in the future answer questions regarding spatial-temporal mismatches of crucial prey for the young of the year herring. To put it in a little bit more detail, we use our response variable as the 50% cumulative spawn, or I'm gonna call that the spawn timing index, which is typically the peak date in the most years. We separated our predictor in 4 categories and applied a hypothesis testing for like a hypothesis testing approach for each one of these categories. For the population, we have spawning duration, spawning stock biomass, the condition factor, that's a function of weight divided by the cubic length, and also the mean age for 3 older fish. That's exactly my spawning stock biomass, my spawning stock, right? For the environmental, we use March sea surface temperature, the SST, April SST, and river flow. For the offshore environmental, we use the Gulf of Alaska SST for fall, spring, winter, fall and winter meridional winds, fall and winter zonal winds, and upwelling index for fall, winter, and spring. For the climatology, we use winter and summer, the multivariate ENSO index, the El Nino South Oscillation, the Pacific Decadal Oscillation, the PDO, the Pacific North American Teleconnection Pattern, the PNA Index, and the North Pacific Gyro Oscillation, the NPGO. We built this set of models for each category or our hypothesis, and we applied the corrected archaic information criteria to choose the best model. And now to the results. Here, I just want to illustrate the spawning timing patterns. The left graph shows the spawning time index, or the day of the year when cumulative spawning reached 50%. We chose this index because it's more robust than the first spawning observation, since that first spawning observation depends on the surveys, and sometimes flights cannot be done because of the weather. So this is like more robust. On the y-axis of this graph we have years, and the x-axis of this graph we have years, and the y-axis we have Julian days. And here I put like an updated version of the graph that I showed previously from Muradian and Trochta, where we have the spawning stock biomass in the y-axis. So the color just illustrates the spawning observation, and we can see here that I highlighted this like higher observation I matched with the other graph that showed like this blue shape. I also show here the date of the year of the oil spill, and we see that even like going to 2020, there is like not much like recovering on this population. It's really depleted, and we're still like trying to figure out what is happening. So for the first set of models, the population-based models, my best model used spawning stock biomass and mean age. So in summary, later spawning with higher spawning stock biomass and older mean age, which is something that we're really thinking about. The mean age relationship is kind of contradictory with what we have in literature, which we might be like an artifact of our the way that we pull the data for the entire Prince William Sound, because we do have like difference between Eastern and Western, and also that can be like what affected this like mean age and show like this like later median spawning with later age. But we're still gonna investigate this further, and I'm gonna show towards like the end of the presentation. The second, for our second set of covariates, the environmental ones, the best model was the April sea surface temperature, where median spawning date decreases with the increase of April sea surface temperatures, which makes a lot of sense because this like temperature is like can be like the most important cue for herring spawning. For our offshore variables, the best model was the meridional wind and upwelling index. So later spawning, as winter upwelling index is weakened, and fall and winter meridional winds are in positive phase. So for the upwelling index, Prince William Sound has a downwelling regime, which can be shown by the negative indexes. However, higher upwelling indexes indicates the more circulations coming from the Gulf of Alaska to the Sound. The upwelling index is a function of geostrophic wind. Although it is derived from Ekman transportation, which contains the wind stress fields, calculated from the zonal and meridional wind components, our analysis showed no collinearity between the variables with like the variance inflation factor below 2, which made us really confident of using both of them together. And just to be clear here, in the x-axis we have winter upwelling index. In the y-axis for both graphs we have meridional wind. In the left one we have fall, and the right one we have winter. And the median spawn date is color-coded, with warmer colors being the later spawning date and colder colors being the earlier spawning date. For climatological, our best model was the summer PNA anomaly. Spawning earlier when there is a positive PNA phase. So just to explain a little bit more, the Pacific North American teleconnection pattern, or PNA, consists of anomalies in the height of pressure surface above mean sea level. A positive PNA phase is associated with warmer episodes in northern Pacific, while negative phases causes colder episodes in the region. So we see here in the graph, the x-axis is the PNA, the summer PNA anomaly, and the y-axis, the median spawning, our spawning index. And we see that with like a positive PNA phase, we have this decrease of the spawning date, so earlier spawning with the positive phase, which makes sense with when we think about the SST. When it's warmer, you can capture this spawning happening earlier. In summary, we have higher spawning stock biomass, and in older the mean age, later spawning date. Median spawning date decreases with the increase of April sea surface temperature, the weakening of the winter upwelling index, and the positive fall-winter meridional wind causes spawning to occur later. And also, a positive PNA phase indicates earlier spawning. So we have here all the summary of what we have from like this preliminary analysis and preliminary part of this study. Moving forward, as I said, I mentioned a lot, and I'm really concerned with this mean age relationship. I want to separate the Eastern and the Western Sound and analyze that separately to see if there is like any, if all the cues are the same for both regions. Here, the two graphs in the right, they were produced by my colleague David, and it's his part of his work that he also recorded this variability between the two regions, like this temporal variability, and it was like different considering the space. So in the y-axis of the graph, we have the days, because I'm calculating this difference from the baseline. It's like this anomaly, so we have like negative and positive values, and we have here capture from like the Eastern and the Western, there is like this variability. So with that, we really want to explore those two regions and do like the same set of analysis for the two regions separately, and figure out what are the cues, what is like causing this spawning phenology for the Pacific herring. So the contributions to the management is to provide a clear idea regarding the covariates, and also that can be used in projecting future population trends. So, and also like I put here this little poster that I made. This is like the new hope, like on the BASA stock assessments, like the Bayesian approach to stock assessments, and like maybe like having this, the results of that be fed into those stock assessments. So we have like a better idea what's going on, what's gonna happen with the population with like this variability. In the end, I want to thank our funding sources, the Alaska Department of Fish and Game for the data collection and processing. Additional thanks to our contributors and everybody that was involved with this work. And I'm leaving here my contact information. Please reach me if you have any questions and suggestions as well. As this is like the preliminary phase of this analysis, I'm really excited about these results that we're uncovering, and I really want to brainstorm with anybody that have experience with phenology and phenology studies to give me some suggestions on this new field to me. So is that, and thank you very much for watching, and I'm like looking forward to more discussions.